Okay, welcome everyone for our second day of the meeting, and it's a pleasure to introduce Blachar from Maryland University, who will tell us about non-community inclusion, exclusion, partial representation of semi-groups, and non-associated groups.
Okay, so thank you very much for the invitation for organizing this conference. So we're going to talk about non-community inclusion exclusion, which is some analog to the usual inclusion exclusion from combinatorics, partial representation of semigroups, and the dispersed polynomials. So first, as a motivation, let's start by considering the space of all multilinear polynomials in non-commuting variables. So this gives us a subspace, and we say that polynomial is Specht if it vanishes under any substitution of the form xi maps to 1. So this Specht.
What do you mean by non-commuting polynomial? There are several possible.
Okay, so the variables don't commute to themselves, but they commute with the base constants. With the constants, yes. So we say the polynomial is Specht, it vanishes under any such substitution. These polynomials appear naturally when you study polynomial identities, because every polynomial identity can be explained by Specht polynomials. So when we want to study the subspace of Specht polynomials, which is, for example, the commutator with Specht, and also we can take the product of the commutator and an iterated commutator. All of them will be Specht polynomials. But if we take a product in this commutator, then it will no longer vanish when we substitute to x1 to b1. Now, there is a nice description of the Specht polynomial. We have an inductive system that helps us to construct all of them, and it's given by higher commutators. So we say that the commutator of two polynomials is a higher commutator if each one of them is either a letter or a commutator or a higher commutator. Okay, so we can take commutators are higher commutator, and we can replace iterated commutators and so forth. And it turns out that so this gives us a full description of the Specht polynomials. So the subset is spanned by products of higher commutators. So similar things to what we saw before.
So it's over Z? Over Z?
Over any field.
Over Z2?
Also over Z. Yeah. Okay, so it spans the products of higher commutators. And also, when you look at the subspace and calculate its dimension, the dimension of the whole space of multilinear polynomials will be n factorial, because we just need to choose the order of, okay, we have n factorial monomials, and it turns out that the dimension of this subspace of polynomials is n factorial over e. And now this number appears also quite naturally in another combinatorial settings, which is the number of derangements. So let's recall the inclusion exclusion. So the combinatorial inclusion exclusion tells us how to compute the cardinality of union or finite union of subsets or the intersection if you take the complement. So the cardinality of the complement of the union, we take the whole group X, we subtract the number of the cardinalities of the sets involved, we add the intersections and then remove triple intersections and so forth. And this alternating sum eventually counts every element exactly once. Maybe the first non-trivial example that you see when we study the combinatorial inclusion exclusion is the number of derangement. So a derangement is a permutation without any fixed point. And how can we compute it? We can take X to be the symmetric group of an element, and we take group AI to be all of the permutations where I is a fixed point. So so the complement, so the union is all of the permutations with some fixed points. So we want to compute the complement of the union, the number of derangements. Any sum here looks like this. We want to look at the intersections of all k subsets. We need to choose which k points will be our fixed points, and then we have n minus k factorial ways to order the rest, which is just n factorial over k factorial. So the total number of derangements is this n factorial over 1 minus 1 plus 1 over 2 minus 1 over 6, which is again n factorial over e. So it seems pretty natural to ask, what is the relation between these Specht polynomials and these derangements? Because if they have the same dimension, can we give some explanation as to why this phenomenon happens? And that was where we started asking the question. And now I'll try to say the whole. I'll try to give you string in 3 or 4 minutes to explain what will happen in this lecture, everything that we're going to say, and then we'll go into the details. So the idea looks as follows. So we take I to be the whole index, the index set, the index set from 1 to n, and for each subset of I, we can take the subspace of multilinear polynomials when we only take variables from S. So when you consider you can define math, okay, so the subspace of Specht polynomials has a natural inclusion in the whole subspace of multilinear polynomials. And then if we want to, and our aim will be to construct a resolution for this subspace. So what we can do is to choose a variable and then substitute it to be 1. And then we reach the subspace of the polynomials of all of the variables without xi. Well, we can actually do it for all I, so we can, what we might also write here is the direct sum of this subspace for any I. So this was the first step, but then we can continue. We can now choose another variable and substitute it again. We can choose an xj and substitute it to be 1, and then we have it less dimensional okay. So n-2 factorial subspaces. Again, we can take the direct sum of all I by nj, and we continue as such. And what we're going to prove is that this complex is actually a resolution for the Specht polynomials. And like so, we can understand all of the polynomials here and compute its dimension because we have a specific resolution. But then the question is, how can we? Okay, first we want to understand it, and how can we actually prove that this gives us a resolution, not just some chain complex? So that will be what we'll try to do today. Yes, we will direct sum here over INJ. Okay, so as any good mathematical problem, the correct way to prove something is to generalize it and then prove something more general. So what we're going to do is to study a specific kind of semigroups, which are called left regular bands. Left regular bands of semigroups which satisfy these two identities. Every element is very important, and also we have this rule u times v times u is just u times v. So if we have an element twice, we can remove its rightmost appearance. These semigroups appear naturally in several places. Okay, when you study semigroups, they appear quite often, and also combinatorics. And maybe as a nice example, we have hyperplanar ring. So if we have in RD, okay, in two-dimensional Euclidean space, several hyperplanes, they divide the whole space into faces. And each face is any intersection, okay, each hyperplane itself divided into 3 parts, the one that's below it, above it, and the hyperplane itself. And any intersection of these things will give us a face. So we have these 2-dimensional faces over here. We have 1-dimensional faces, which are the intervals on each hyperplane, on each line here. There's 0-dimensional, which are these points. And we can define a product on this set of faces as follows. Suppose we have 2 faces. Well, here they're both 1-dimensional. We can do it for any 2 faces. And the idea is that if we want to multiply x and y, we choose a point in x and a point in y, some point in the interior, and then we try to go a small positive step from x to y and see where we land. So here, if we go from x to y, we do a small step. What we really get is all of this face. So x times y will give us this 2-dimensional face. And this is also collecting the fixed product. And now we can just verify that all of these, both of these identities hold. Well, everything is like important because if I start at x and go towards this x and just stay in x, and if I go from x to y and I try to return to x, well, I go from x to y, now I'm here. And if I choose a point in x1 and try to go back to x, well, I just stay in this area. So this can be proven also generally, but this gives us one example of left regular bands and where they appear. So now we can also define the free left regular band, which will be just the semigroup generated by its n-idempotence, will be denoted by Fn, so each of them is idempotent, and we have this rule, the left regular band rule, that when we multiply distinct elements and they multiply again by something, we just erase it. Okay, and so the elements of Fn are just this order the product of the EIs and the cardinalities e times n factorial. We just calculate all of the proper cardinalities. Now, a nice model for the free left regular band is what's called the setting library. It also gives us a nice Markov chain. For those of you familiar with Markov chains, and the idea is followed. We can just think of it as an action of the free left regular band in the symmetric group. And the action is given as such. We're looking at the library. This library has only one shelf with n books, and in each step, what we're doing is we choose some book and we take it out and put it back at the end of the shelf. So each step we choose a book and put it back at the end of the shelf, and then so we can just take the operation EI. So we take the ith book and return it to the back, and this indeed defines again the left regular band, right? Because if I do it, so again everything is then reported. If I take out book I and then take book J and return it, and then when I take out book I, I didn't have to take it in the first place. Right? It's just transparent to what we're doing. So this is a nice model which will also relate it to the Specht polynomial problem. So let's recall that VI is a set of multilinear non-commutative polynomials in variables. And now, when we try, so we can do something really similar to the setting library. We can define these elements, Ci of f. We substitute one instead of xi and move xi to the back. So this is just a setting library interpretation for the case of Specht polynomials. And any Specht polynomials will just vanish, just in the kernel of each of these elements. So they form a representation of the free left regular band. You can just check all of the relations. And these are so this is also just presented the absolute kernel of this representation. Just anything that will vanish under all of these substitutions just means that any substitution will vanish, and then this is exactly the absolute kernel. So we took the initial problem of studying the Specht polynomials, and now what we really want to do, we take a representation of the free left regular band and try to build a resolution for its absolute kernel. Questions so far? Okay, so the way to do it is what we really want to do is to take a representation of this of the left regular band, and just expand it to a partial representation of a bigger semi-group. And the idea to do that is that when we consider the previous example, we can take the operation of EI and just write it as a composition of two operations. We can just first substitute one for xi, and then we can multiply by xi from the right. So EI is just the composition of these two maps. We can just think of it as we can take out a book and not return it in the meantime. We can take it out, return it later. So this gives us a decomposition into two maps. But what we should be careful, because they are not defined everywhere. Pi is only defined when xi appears in F, and the other is only defined when xi doesn't appear in this polynomial in G, right? Because we want to stay in the set of multilinear polynomials. So they're not defined on the whole space, but they are defined somewhere. This gives us a partial representation of bigger semigroup generated by AIs and BIs with these relations. Okay, so AI corresponds to mu I to returning the book, and BI corresponds to taking it out. So if I return the book, take it out, and then return it again, I just return the book. If I take a book out, return it, and take it out again, I just took it out. Taking out two books commutes. So BIs are just taking out two books. It doesn't matter in which order I do it. And each BI commutes with AJ for distinct elements. If I take a book I and then return a book J, well, I could also return J and then take out I. So we expanded our free left regular band to a larger semigroup and got a partial representation of this semigroup. And from the relations, we can also make sure that Okay, so this is again the semigroup. It follows that this semigroup is quite large. It contains 3 semigroups. It's a semigroup. Those generated by the AIs, it's a 3 semigroups, but products of AIs and BIs are just idempotents. It just follows from this relation, for example, if you multiply by BI, this gives us an idempotent, and we can make sure, and then we also have, and then we can also consider Fn as a subset of Qn. Fn is naturally embedded in Qn by taking EI to be this AI BI. So again, like the motivation we had, each EI was taking out the book and then return it. So we can first take it out and then return it. So we can take this left regular band and then extend this representation specifically to Qn. So that will be the main idea. What we'll try to do is basically the same. We'll try to take a general representation and exactly expand it to a partial representation of Qn. Okay, so we won't get a general partial representation. What we will get is some special representation, which we call a cubical partial representation. And how can we describe this? It's a cube of spaces. We have this PS for any subset. So think of PS as again multilinear polynomials and variables that appear in S, with perhaps phi I that knows how to take out an index I, and mu I which knows how to return index I, with the exact same relations we have. Right, so when we multiply pi j times mu j is the identity of this component, and if we return a book and then take it out, then we basically did nothing. That's the first relation which we want. The second relation is again that taking out one book and returning another, they commute. And okay, and well, it will look like this basically. There should be also the things that the pi's commute. Yes, so there's a small thing here. The taking out books commute, and we try to look at this representation. Basically looks like this. So we have these two spaces for n equals 3, and each line here corresponds to two functions, two operations, one which takes us down and one which takes us up. And again, going down in 2 ways just commute. So if we go from here to here, commute. And if we take out 2 and then return 3, then it will be the same as returning 3 and then taking out 2. But going up doesn't necessarily commute. So going from 1 to 3 doesn't necessarily commute to take anything into 1. So these are the kind of partial representations that we're interested in, because they basically resemble the example, basically just like the example of the Specht polynomial. Like we have the whole space of multilinear polynomials in all of the variables. Here we have the subspace of multilinear polynomials in some of the variables. Here we have just basically is itself. And this induces a partial. Okay, so we have a representation of all of Fn on all of this on the large space, but the partial representation of Qn on this direct sum. The partial representation, what it basically means, each element has an operation, but it's defined only on subspace. So each EI is only defined on the set which contains I. So each element is only defined on some subspace of this whole big space. And also, when we compose 2 elements, okay, so we compose 2 elements and just only when the composition is only defined where they're both defined. So if we try to compose phi and phi j, this is defined only on sets which contain both I and j. So this is what we mean by a partial representation. And it turns out that these are precisely that any representation of so anytime such thing gives us a partial representation of Qn and full representation of Fn, but it turns out that we can also take any representation of Fn and just extend it to this kind of cubical partial representation. So each representation, if we started with Specht polynomials, we could have constructed this whole resolution of spaces with this whole cube of spaces of what will be just like the polynomials in the appropriate variables. Okay, so how does the equivalence work? Suppose we're given some representation of Fn generated by n idempotent maps. Let's from epsilon 1 to epsilon n. And again, we should just think of them as this taking out a book and then return it, or substituting one and then multiplying it by the right. So let's begin with a nice proposition on left regular bands. The kernel of the product doesn't depend on their order. Although the product is different in the semigroup, and also the product of the operations might be different, it's different operations on the space, the kernel is the same. And why does it work? Because of the relation of the free left regular band, if we have something in the kernel of this operation, then when I multiply it by epsilon I1, multiply by epsilon I1 to epsilon IT in that order, well, epsilon IT appears somewhere here. And because this is a left regular band, we can just remove this epsilon IT from its appearance here. And the epsilon IT is here. And epsilon IT minus 1 again, it appears here. So we can just remove each of them because it already appears in this product. And what we really get is the remainder of this product. So that means that although the products may be different, they still have the same kernel. Okay, so because they have the same kernel, this map is defined. Not that you take the product of the F and apply to X, and then you can just permute the order as you wish. This is well defined. And then how can we use this to construct a few spaces? Well, let's write epsilon of S to be the product. So of the epsilon I, when we multiply them by the natural order. So we just multiply from the smaller I to this side, to the greater side, just to keep it consistent. And that's that will be nice to remember. And now we can really just define the subspaces. So maybe I'll use the board a bit. So we have this PS is epsilon of S bar is complement of S times V, which means that let's take, for example, S equals, okay, let's take it 1 to n minus 1, and let's return to the example of multilinear polynomials. So epsilon of S bar is just epsilon of n, which is just substituting 1 for xn and then return it, then putting it on the right. So when we apply epsilon of n to vi, what we really get is v of 1 to n minus 1, and then xn at the end. So we can just think of it as multilinear polynomials in this variable, because xn doesn't really, it will just stays in the rightmost space, so it doesn't really change, doesn't really matter for us. And if we do it again, so whenever we have this, generally it's epsilon of s, this complement times vi, what we really get is vs times this, let's call it xs bar, just the product of the x's, xi1 to xit. This remain fixed in the same order, and therefore what we get is something that is isomorphic to vs. We're just talking as vector spaces, but to get vs to be just to resemble this vs. Okay, so how do we encode substituting one for an element? We just multiply by epsilon I, well, in the right place. Okay, so again, I might be somewhere in between the element of S bar, but we can just think of it as putting it in the right place. So if you take here pi of 1 of something that appears in this element, so epsilon n of vi, what we really want is this epsilon of 1n times vi, which is epsilon 1 epsilon n vi. So what we really get is again v I minus 1 and then times again, okay, we have the xn and x1. Yes, but we still don't really see the x1 because this element, because okay, because everything that only matters is the order of these monomials, these variables. And the last, okay, in the last map again, okay, in the last map, mu I is the map that's supposed to return to put I back at the end. So what we do is, so we consider mu1 of this space, mu1 acting on epsilon 1, epsilon n of vi, this is just epsilon n, epsilon 1 of vi. And because this map is well defined, as we said before, then this mu is well defined, and what we really get is this vi minus 1 to n, and then x1 moved to the right place, and xn is here. So this gives us exactly what we want. But this is for the Schmidt example, but generally these elements indeed satisfy the relation. This gives us a cubical partial representation of Qn. So that's basically the idea of the equivalence. We can take a full representation of this free left regular band. We use these idempotents, these epsilons, to decompose the space V, to extract from V these subspaces, P of S, by applying the epsilons outside of S, just removing F the order variable, and then we have these pi's by adding the epsilon I somewhere that doesn't really matter, and ui puts it back in the right place. Okay, now we can construct the resolution for this absolute kernel. And the resolution looks as follows. Suppose we have such a cubical partial representation for a frame, and we take exactly the direct sum of all of PS, and just multilinear polynomials in k variables, whichever k variables you want. Now the absolute kernel, this k, which is the intersection of all of the pi j, is exactly the kernel of this map. That we can just take the alternating sum of this pi j of f, and because this is the direct sum, the absolute kernel, the intersection of the kernel is just the kernel of this map. Okay, so this gives us the first step in the resolution. And, okay, complex for this slide. And then we can find the rest by defining this d of k plus 1 on elements from k plus 1. This is just the sum of multilinear polynomials. We can just do exactly this idea for each monomial by itself. So for each one, we take this alternating sum of substituting one in the right order. And when we have this chain complex, it just means this complex is exact. We can just take there are some things to verify, but it turns out this complex is indeed exact. Okay, this is characteristic prime to n factorial, but exactness is the first component here, n minus 1 actually holds characteristic 3. And that was the material that we wanted. It is worth mentioning this is only resolution of vector spaces. Everything is just vector space. For example, in the setting library, because we're dealing with multilinear polynomials, there are also modules over Sn. So Sn modules. And well, Sn acts naturally on the free left regular band by permuting the generators, and also on this subgroup, this Q of n. And then, if it also acts on nicely on these pi's and these homomorphisms, then we can also become a resolution of Sn modules. But generally, they're just vector spaces. So let's see some applications. Okay, so one nice application is as follows. If we have a polynomial, we can just think of substituting one for a given subset of the variables. So we can just choose any element from S to be 1, or not from S to be 1, and we get some polynomial, some multilinear polynomial in the variables that only appear in S. And then we can ask, if we have such a system, when does it have some big polynomial that explains it? Okay, so naturally we have some necessary condition. We really need to agree on the intersections, right? If we take two S1 and S2, if we intersect, and we want that when we substitute ones and go to a polynomial in the intersection, we want them to agree to get the same polynomial. But generally, how can we really make sure that there is such a common ancestor? Turns out that this intersection is exactly also a sufficient condition. Right? But if we have such a family which is coherent, meaning that it is on all of the intersections, when we substitute elements to get to the intersection, get the same polynomial, then this family has a common answer. So it has some big polynomial that explains it. Okay, so it's written without any characteristic assumption because this holds for every characteristic. It really only uses the exactness of the first step, the Pn minus 1. Because what we can really do is just go step by step. We don't need to go from K to all of the polynomials. We can just take these polynomials in K variables, leave them to K plus 1, leave them to K plus 2, do each step by step. And because of the exactness of the Pn minus 1 holds in every characteristic, then we'll just get this common answer for all of these polynomials. Okay, so that is one application, and another one is to calculate the exact dimension. What we said at the beginning, the dimension of the Specht polynomials in any cubical partial representation. Because we have such a resolution, then we can calculate the dimension of K just as the alternating sum of dimension. And if we return to the example that we had for Specht polynomials, Pi is all of the variables, all of the polynomials which are multilinear in I variables. So what is the dimension? We choose which I variables and then choose the order. So this is n factorial over n minus 1 factorial. And when we substitute it in this formula, we get exactly this n factorial over e. Exactly the same dimension. So this gives us some explanation. We have some resolution for the space, which exactly gives us its alternating sum of n factorial over I factorial. There is still a nice question for those who are interested. Can we also give some combinatorial explanation, which is some finding nice basis elements for the Specht polynomials, or some more direct connection between the arrangements and the Specht polynomials? We don't have such an explanation, such a constructive explanation yet. Okay, so until now we handled the associative case. So you see that I'm way ahead of time, so I'm sorry it's a bit shorter. But let's talk a bit about the non-associative case, the case of non-associative polynomials. So what do I mean by non-associative polynomials? So again, we have these variables. They don't commute, but also don't associate with each other. They do commute and associate with the basis. So the scalars associate with everything and commute with everything, but each monomial just can look anything like a product with parentheses as you wish on these variables. And again, we can give the same definition that the polynomial is Specht if when we substitute it in one, for any substitution, the polynomial vanishes. So what can we say about this? Okay, let's say a non-associative example will be taking the associator. The usual associator will be Specht because one associates with everything. So exactly just like the associative case, we never use anything about associativity. They still form cubical partial representation. We just need to add many parentheses everywhere, but it still works. Everything is still holds. So we can conclude, we can write an explicit formula which we call the Catalan numbers, but eventually the dimension of the subsets of the Specht polynomials will go to something like this dimension times e to the minus quarter. Before it was e to the minus 1, but now it's e to the minus quarter because of this Catalan number, which asymptotically is like 4 to the n. So they give some larger subspace of these non-associative polynomials that maybe a natural generalization of the second fact we said before doesn't hold anymore. And what is this fact? That they're no longer generated by taking these higher commutators. So something else happens in the non-associative case. If before all of the associative Specht polynomials could be explained by this inductive system of defining the higher commutator and taking products and iterated commutators and whatever we want, then it doesn't work anymore, even if we add associators. And for one example, we can take this polynomial which is the associator of A, B, and C times D minus this associator times D and this associator times C. This is Specht. Well, in A and B, it's clear because all of the associators will vanish. But if substitute C, for example, to B1, you get here the associator of A, B, and D. This will vanish, and here we get again A, B, and D. The same will hold if we do it for D equals 1. This is the associator which will cancel out this associator, and this will vanish by itself. So this polynomial, this is one example for a polynomial which is Specht, but isn't generated in a similar fashion as the associative case. The commutator and the associators really need something bigger. We also calculated the dimension of the Specht polynomials for small n's when it was 2 to 5. So for, this is the dimension of the subspace, which is generated by these commutators and associators. So for n equals 2 and 3, we just agreed. We don't have anything to be different. But for n equals 4, we get several examples of this form. And for n equals 5, it goes even more. And if we try to add also this polynomial, we said, okay, maybe this is one exception. We need to have this V4 polynomial as another generator of an inductive system. It still doesn't work. We still have something new in n equals 5, and it seems as though although we don't have complete proof, it seems as though we won't have this finite set of operations that we can really use. We have some operation that takes a general polynomial and makes it a Specht polynomial, it's called Spechtization. However, it's not yet clear whether there are some finite set of elements which can explain, just like the commutators explain everything in the associative case. In the non-associative case, it's still unclear whether we have some ideas, but not something complete. Whether this is enough, whether this is enough to generate all of the Specht polynomials, or also if there is some polynomial or something really complicated that somehow manages to avoid this process. Okay, so again, I'm sorry that I finished a bit early, and also forgot to mention again, it's joint with Louis Rowan and Kuzevishna. I forgot to mention it before. I think I'll end here. Any questions?
I don't understand the connection between the rearrangement of books that we have. For example, we have 1, 2, 3, 4.
Again, what?
The connection, I think you said that isomorphic, so the bus band and the rearrangement.
The hyperparameter arrangements?
Of the bookshop rearrangement. Well, I don't.
This one?
No.
The books. Sorry. The setting library? This one, the setting library example?
Yeah. Project 1, 2, 3, 2.
If we have a library with 3 books, 1, 2, 3. So when I apply, for example, E2, then what I get is I take the book 2 and put it to the end of the shelf, and we have 1, and then we have 2, and then we have 2. So when we apply, let's say E3, we actually return to the original position, 1, 2, and 3. But when we apply E2 again, it doesn't really matter.
The operators.
Each of them is an idempotent. We apply E2 again, then we just remain the same. When we put E2 and then E3 and then E2, this will just be done.
Perhaps if you can scroll back to slide number 20. It's highly unlikely that you should expect the commutators and associators to work for general and associative polynomials. But if you try to consider alternative polynomials, that makes more sense.
Some additional identities.
Yeah, like you have a free alternative algebra generated by any number of generators you want, and that would be a better candidate for studying such questions.
So we haven't considered that, but it's a good idea. So, think of
I have a question. So the resolution, we said that it is exact if except in for small primes, if we're dividing into tutorials. So do you know it is not exact?
we don't know whether it's we don't know that it's exact.
We just don't know.
Yeah, we just don't know. Yeah.
The original formula for the dimension of the Schreck polynomials holds in any characteristic.
Yes.
Okay.
Yes.
I think this example is such a pretty long for everything. It's still so that's complicated. Because in alternative algebra, any I mean, associate power will want to do.
So we can think about it. It's interesting to think about the alternative polynomials. Yes.
The correlative one is a so-called of complex mix extra power. That complex generalize and also complex. Similar to the version of this. I think maybe relatively with n factorial with this complex and depending on the symmetry powers or complex power. Symmetry powers will contribute to this extent because it's n factorial. Similar to the moment of this can be
So it's interesting. Thank you very much.
Okay, so let's thank Guy again.